The history of X-rays is one of the most fascinating stories in the development of modern science and medicine. A journey that begins with a curious discovery in the late 19th century and has since grown into a cornerstone of medical diagnostics, industrial inspection, scientific exploration, and even art authentication. And to understand its significance, we must go back to November 8, 1895, when a German physicist named Wilhelm Conrad Röntgen was experimenting with cathode rays in his laboratory at the University of Würzburg, Germany, and while passing an electrical current through a Crookes tube, a type of vacuum tube, he noticed that a fluorescent screen coated with barium platinocyanide across the room began to glow even though it was shielded from direct light. And realizing that some form of invisible radiation must be penetrating solid matter and causing this fluorescence, he began systematic experiments and within weeks discovered that this new form of radiation could pass through materials like wood and human tissue, but was stopped by denser substances like bone and metal, creating shadow images on photographic plates. And since he did not know the exact nature of the rays, he called them X-rays, with X representing the unknown. And within days of his discovery, he produced the first X-ray image in history, that of his wife Anna Bertha's hand, which revealed her bones and wedding ring. And upon seeing the image, she famously exclaimed, "I have seen my death," reflecting both the wonder and unease of this new window into the human body. And by December 1895, Röntgen published his findings in a paper titled On a New Kind of Rays, which spread rapidly across the world, stunning the scientific and medical communities. And by January 1896, newspapers were already reporting on pictures of the invisible, and physicians were experimenting with X-rays to look inside the human body, marking one of the fastest adoptions of a scientific discovery in history. The impact of X-rays on medicine was immediate and profound because for the first time in history, doctors could see inside the living body without surgery, making it possible to diagnose bone fractures, locate bullets or foreign objects, and study diseases in ways previously unimaginable. And hospitals across Europe and America rushed to acquire X-ray equipment, with military doctors using them as early as the Greco-Turkish War in 1897, and later on a large scale during World War I to locate shrapnel and broken bones, saving countless lives. And while the medical benefits were enormous, the risks of radiation were not yet understood. And in those early years, doctors, physicists, and even curious lay people exposed themselves to X-rays without protection, often leading to severe burns, hair loss, and cancers, with early pioneers like Clarence Dally, an assistant to Thomas Edison, suffering fatal consequences from repeated exposure, becoming one of the first known victims of radiation-induced cancer. Yet despite these dangers, the technology advanced rapidly, with manufacturers producing portable X-ray machines and researchers refining techniques to improve image clarity and reduce exposure times, leading to the development of radiology as a new medical specialty. With the first radiology departments appearing in hospitals by the early 20th century, and by 1901, Wilhelm Röntgen was awarded the very first Nobel Prize in Physics for his discovery of X-rays, cementing his place in scientific history. As the 20th century unfolded, X-ray technology evolved from crude machines into highly sophisticated diagnostic tools with the invention of the Coolidge tube in 1913 by William D. Coolidge, which used a heated tungsten filament to produce consistent and controllable X-rays, replacing the unreliable Crookes tubes and becoming the basis for modern X-ray tubes. While advances in film and screen technology allowed sharper images with lower doses, and fluoroscopy, pioneered by Thomas Edison in the 1890s and later improved, enabled real-time moving X-ray images, which became essential in cardiology and gastrointestinal medicine, allowing doctors to observe organ functions dynamically. And further breakthroughs came with the use of contrast agents like barium and iodine compounds, which enhanced visualization of soft tissues. blood vessels, and internal organs, expanding the reach of radiology far beyond bones and fractures. While in parallel, X-rays became indispensable in dentistry, with dentists using them to detect cavities, impacted teeth, and jaw problems, making dental X-rays a standard procedure by the mid-20th century. Outside of medicine, X-rays found diverse applications in science, industry, and security, with one of the most important breakthroughs occurring in 1912, when German physicist Max von Laue discovered that X-rays could be diffracted by crystals, proving their wave-like nature and giving rise to the field of X-ray crystallography, which became a powerful tool for studying atomic and molecular structures. And in the decades that followed, X-ray crystallography played a key role in some of the greatest scientific discoveries of the 20th century, including the determination of the structure of DNA by James Watson, Francis Crick, and Rosalind Franklin in 1953, a milestone that revolutionized biology and medicine. While in industry, X-rays became vital for non-destructive testing, allowing engineers to inspect welds, engines, pipelines, and aircraft components for hidden flaws, ensuring safety and reliability in critical infrastructure. And in security, X-rays became essential tools for screening luggage and cargo, especially after the mid-20th century, and later intensified after the events of 9/11, when airport security around the world adopted X-ray scanning as standard practice, keeping millions of travelers safe each day. As medical imaging advanced further, X-rays served as the foundation for even more sophisticated technologies, with computed tomography, CT, emerging in the 1970s, pioneered by Godfrey Hounsfield and Alan Cormack, who developed scanners that used X-rays combined with computer processing to create detailed cross-sectional images of the body, giving doctors three-dimensional views of internal organs, tumors, and injuries, transforming diagnostics and treatment planning. And CT scans soon became indispensable in emergency medicine, oncology, and neurology, offering life-saving insights. While digital radiography began replacing traditional film in the late 20th and early 21st centuries, allowing instant image viewing, lower radiation doses, and easy storage and sharing of images across hospital networks, enhancing both efficiency and patient safety. And new advancements like dual-energy X-rays enabled bone density measurements to diagnose osteoporosis, while interventional radiology used real-time imaging to guide minimally invasive surgeries, proving that X-rays were not just diagnostic tools, but active participants in treatment. With great progress came the need for greater safety, and over time protective measures were introduced, including lead aprons, thyroid shields, dosimeters for monitoring radiation exposure, and strict regulations by organizations like the International Commission on Radiological Protection, ICRP, ensuring that patients and healthcare workers were safeguarded while still benefiting from the incredible diagnostic power of X-rays. And these measures dramatically reduced risks while maximizing benefits, enabling X-ray imaging to become one of the safest and most routine procedures in modern medicine, performed millions of times every day worldwide. Today, X-rays continue to be one of the most widely used imaging technologies, forming the backbone of radiology alongside MRI, ultrasound, and nuclear medicine, and they remain irreplaceable in fields ranging from dentistry to oncology, from orthopedic surgery to cardiology. While in science, X-ray crystallography and synchrotron radiation facilities allow researchers to probe materials at the atomic level, driving innovation in chemistry, nanotechnology, and drug design. And in security, advanced X-ray scanners with 3D imaging and AI analysis provide powerful tools for law enforcement and transportation safety, ensuring both efficiency and protection in an increasingly complex world. And looking ahead, the future of X-ray technology lies in further reducing radiation doses, enhancing digital imaging, integrating artificial intelligence for faster and more accurate diagnosis, and combining X-rays with other modalities to create hybrid imaging systems that can provide unprecedented levels of detail and precision, ensuring that the discovery Röntgen made in 1895 continues to save lives, advance science, and secure societies for generations to come. From the accidental glow on a fluorescent screen in Röntgen's lab to the advanced scanners mapping our bodies today, the story of X-rays is a remarkable tale of curiosity, innovation, and transformation, a discovery that opened a new window into the invisible, revolutionized medicine, advanced science, and made the hidden visible, proving once again that human ingenuity has the power to change the world in ways once thought impossible.